Welcome everyone. Thank you for joining this presentation on data security quantification. Today I will present an overview or a literature review, what I studied or what I searched during this 4 months, recent 4 months. And also I will talk about the future directions or about during these 4 months I detect some research gap. So I will work on one or many research gap as a future direction. So today only I have an overview, simple overview about what I did. Data security quantification is so important because or why we need to quantify data security or why the data security quantification is so important, because as we know the complexity of cyber attacks increased, and we need for a measurable risk assessment, and also we need to bridge between the theory and practical strategies, and also we can the must benefits of the data security quantification. Also we can estimate the budget or the cost according to the impact of or effect of the attack. So the agenda of this presentation, we will overview of some major approaches. Actually, once I studied my research or once I studied many research papers, I categorize it into many categories, or depends on the principle or depends on the model. In this discussion of each category, I will discuss these categories depends on an example, because it's easier to understand better and better than to explain a theory ideas. At the end, we will compare these categories, and we will talk about the future direction. The major approaches, I mentioned only 5 main approaches, but also in the real life we have more than these 5 approaches. The first one is probabilistic and statistical modeling approaches. The second one, game theoretic approaches, stochastic processes and transition approaches, machine learning and data-driven approaches. At the end, we have integrated and hybrid approaches. That before we start, there is an important consideration. Once I did this literature review, or once I started my studies, I ignored the side field. That means we can apply these approaches in many contexts. So it doesn't matter if we applied these approaches in organization or on hosts or servers or application or vulnerability. We ignore the cited the subject of site or the scope of implementation itself. So for example, here in probabilistic and statistical approaches, we have many studies. The first one is designed for the organization in general. Second one for networks, focused on networks field, hosted server software applications and vulnerability. That's we proposed we can, with some modification and customization, we can apply any one of these approaches on another one. So we ignored the scope of implementation. We focused on the model or on the approach itself. First one, probabilistic and statistical modeling approaches. In general, we use cumulative distribution. We use matrix. This is the tools or main concept in the statistical and probabilistic modelings or models. So as I said before, I will explain the approach used depends on an example. The example will be a research paper. The researcher here in Ni and others designed a model depends on statistical and probabilistic modeling. Here in this research paper, they used in serverless computing. But as I mentioned before, it's not. We will not focus on the field of the implementation. We will focus on the mentality or the methodology itself, because we can, with some modification, we can apply it in another field. The framework for this researcher, first of all, they designed an attack and defense tree. For each attack, they calculated like a matrix called risk matrix. And depends on this statistical concept, they calculated the probability of each risk to risk assessment. At the end, they calculated the matrix or a new value called mitigation matrix. How we can reduce the impact, or how we can to reduce the effect of this risk or this threat. They suggested this risk like relative risk matrix value, vulnerability severity, consequence impact, and exploitability. Here, there is definition for each concept, and also there is like a scoring for each definition. For example, for consequence impact, we have low, medium, high, extreme. If we have the risk, the consequence impact of the risk is low, we will give number 1, like a score or yeah, like scoring. For the mitigation risk, also we have mitigation degree visibility and implementation simplicity. Also, this is factors scoring by the expert with the same factor table. The first, as I mentioned, this is research applied for the serverless computing. As we know, the serverless computing, we have 4 layers: access layers, cloud layers, infrastructure layers, and physical layers. So the here, if we will talk about the infrastructure layers, it's basically it's contained from 2 type of or 2 main component: containers and Kubernetes. The main attack of container, they modeling in this tree, for example, exposed secret, insecure networking, and so on. Also for the Kubernetes, here, if we will talk about the exposed secret here and insecure networking, we will go to the previous matrix, this risk matrix. We have VS and CI and E. They give the expert here, they give a score for example, exposed secret is 3, number 3. That means it's high. For CI2, it's medium, and E means it's medium. The depends on their matrix or depends on their proposed concept, it's equal 12. If we will calculate the standard value, it will be 1.02 and probability 0.84, depends on the statistical and the probabilistic concept. We will calculate the mean. It's not so important to focus on the formula, but I should to mention how they calculated. The mean is equal 9.53 and standard deviation, and they calculated SV for the first attack. As an example, it will be equal 1.02. They converted to a probability using Z table, or in some reference called Z score. So the probability of first attack, it's equal 0.84. And they recalculate these steps for all the attacks in the rest of the tree. Here, the expert also, they suggested the solution or what we can do for this risk to mitigate the impact or to reduce the impact on our, for example, organization or on our network. Also, they calculate the probability of each solution or of each mitigation solution with the same steps. For example, if we will talk about the exposed secret, the solution or to avoid it or to reduce it is rotating secrets. So we will calculate the probability of rotating secrets with the same step, 0.62. So this is the attack defense tree at the end. So for each approaches, we have advantages and disadvantages. So we will focus now on the limitation of each approaches, because we will work on the limitation, how we can solve or how we can improve later. So the limitation of this approaches, or for this, for this category in general, dependency on expert judgment and assigning scores. The second one, the complexity, because we need to recalculate for each attack and for each solution, and there is no practical evaluation and verification of a quantitative accuracy. So we don't know the result is it accurate, or how accurate are the results. So this is the main challenge for this research. So the second approach is game theoretic approaches. In general, game theoretic or game theory, it's study the interaction between two groups, how the behavior of the first group will affect on the second group. Also, in any game, we have three main elements: the players and action and payoff. The type of the game theory, we have many types: cooperative game and no cooperative and sequential and so on. The example here in this approaches, actually I studied many research papers for each approaches, but I mentioned only one example. That means only one research in this slide. So here's Lee and others. They suggested this research to quantify the vulnerability and security, or the data security, especially in the social Internet of Things. The step one, they model the game theory. They identify the players between the attack and the security team or the security admin. They mentioned that the game type is a no cooperative and sequential game. The model contains two types: state and action. The state is the result of the action, and the action, what is the behavior of the attack or the security team or the security admins. And they build their tree. And initially, this is the tree of the game theory. The state A1, this is the initial state. The initial state means the system, there is no attack or no threat, and also there is no security policy applied yet. The second step, they calculated the cost of impact for the attack, and they calculated the cost of the action has been taken by the security team. So the attack, also, it's not so important to focus on the math for equations, because, but I should to mention how they calculated the cost. So the attack, the main attack equals all the sub attacks costs in the tree. Also here the effect. We need to calculate the effect of the attack and the effect of the action for the security team, because we need to calculate the impact. So calculating the effect is a part of calculating in the impact, but in impact we should to weight depends on the CIA, the confidentiality, integrity, and availability. The third step is the payoff calculation. Payoff means the gain. For example, if the attack applied an action, what is the gain will be for the attack? And the vice versa for the admin teams, or so for the security admins or security teams, if they applied a security policy or they applied something new in the network or in this organization, what is the payoff we will gain, or we will get it? So the attack payoff will calculate using this formula. In the payoff of the security team will be the inverse of this formula. And here there is like a simple constant is lambda. Lambda, that's all the prior defense actions. Sometimes we will apply a general security policy. This policy will mitigate or will reduce the impact of the attack, even if we don't if we don't do this policy for this specific attack or for this specific risk. Also, we can calculate the lambda using this equation. This is, I said, the security administrator's payoff is the inverse of the payoff attacks payoff. this is illustrate. I think I bring case study. This is the case study. The subject of the case study is smart home area network. We have a network for the smart home. We applied those attack on this network. So the DOS attack involves three main actions: installing a root device. Root device means unauthorized device, compromising an installed device, and damage target. The security action they applied to reduce or to avoid this risk, changing the device's configuration, changing the network configuration, and applying IDS. So we'll take only first action to and illustrate the value to make the research is more clear. This is a tree. Also here I should to mention the values or the numerical values based on the CVE. CVE, this is like public data set available on the internet, categorize the vulnerabilities in general. So I think it's popular for majority of you. So they depends on all the numeric value depends on this CVE data set on the internet. So, this is three action for the attack: compromising installed device. They calculated the effect is 14.3. The impact is 14.3. The security team or the security administrator applied an action changing device configuration. The effect of this is 8.3. And the lambda for the previous security policy or security step is 2.1. So if we will fill this information in the tree, it will be like this. If we will study only one action, initial state it was 0. Once the attack compromise installed a new device or unauthorized device, the impact of the or the payoff of the attack will be 14.3. Depends on the table. This value will bring it from CVE dataset, and the security administrators changing device configuration. The impact of this step is 8.3, and lambda, as we see it's equal to 2.1. The security payoff it will be in the second dips minus 3.9, because minus 14.3 plus the changing device configuration impact plus lambda it will be minus 3.9. We will, as we can see here, in the first dips it was minus 14.3, but in the second it will be minus 3.9. That means we increase the security payoff, and we in this research the attack payoff is still as it is, minus 14.3. Sorry? Yeah, minus 14.3 plus the plus here. Sorry, by mistake. So the limitation here, I will focus on the limitation, depends on the public available data because they depends on CVE. Okay, and there is also lack of verification and evaluation the quantitative accuracy of the result. We don't know this value, how much is accurate. It is accurate, but we don't know how much, or there is no model checker to verify is it okay or not. The third approach is stochastic process and transition approaches. This is it's similar to the previous approaches, but before we talk the state, we will move from the state to another state, depends on the payoff or depends on the calculation. Here we will depends on Markov chain or stochastic concepts. So here, as I said, a series of state transition over time. The main step, we will define the state, the main state, and then we will create a matrix to present the probability of moving from a state to another one. At the end, we will calculate the matrix over the time. Here, I will not explain more about it because, as I said, it's similar to the previous approaches, but the mentality, it's a little different. Here the researcher, Wang and others, assume that we have 7 states. security state, vulnerable state, attacked state, degenerate state, failure state, positive state, and negative state. And moving from security state to security vulnerable state depends on the, for example, if we have a website and there is abnormal activity to enter the password more than 5 times, and all of them are wrong. So the website will take an action to deny the user enters the password after, for example, half an hour or 1 hour. So once the user enters the wrong password, we will move from the security state to vulnerable state. Once the website take an action to avoid the user or to deny the user enters the password, for example, half an hour, we will move from vulnerable state to security state. Also, they mentioned how they calculated the security level for each state depends on this formula. And here, because depends on the continuous time Markov chain, it depends on the time, also the communication delay. So they suggested two constants, alpha and beta, to give the the focus on the important factor. For example, if we have in our system, we have the time is matter, or the time is so important, we will give beta high value. If we have the time is not so important, we will focus on the security operation, we will give alpha high value and high value. But the summation of alpha and beta equal 1. Here, and at the end, they assume threshold if the t related to 0.7 as a security operation, and the time or communication delay is equal 1. That means we will move to, if we are in security degenerate state, we will move to security state. Suppose the threshold equal for security operation equals 0, but the communication delay is 0.2. We will move to the security, so to the failure state. Oh, sorry. The limitation here also computational heavy. And as we can see, we use the weighting coefficients like alpha and beta and threshold. This is already fixed, and this is already defined by the researcher by assumptions. So with the real time or real world system, it will not be good. The fourth approach is machine learning and data-driven approaches. Also, in general, this is approaches use historical data like dataset to learn the model or to learn the classifier. The methods, we have many methods: classification, clustering, and even association, regression, anomaly detection. The main step for all these approaches, we should to determine the resources, our data set. Second step, we will process or pre-process this data set. Then we will build our construction. We will validate and test the model. At the end, we will test this model in real life or in real time risk or in real time world. Here, the Sarabi and others researchers proposed a methodology to quantify data using the data security using the machine learning and data driven. The methodology has 4 main states: data collection, pre-processing, model construction, and evaluation. The data collection depends on 4 data sets. Also, this data set available on the internet. There's the vocabulary for event recording and incident sharing. AWIS, this is from Amazon Web Services, and also ODP and Neostar provides. Each one of them, it's provide a specific information or specific data we needed to build the construction. For example, this is general sample or general example for each one of the data set. The second step is pre-processing. Pre-processing has 3 main steps also: domain standardization, If we have sometimes subdomains like mail.google.com, we will convert it to main domain like google.com. Missing data, if we have zero, so for example, if we don't have value, if that column is numerical field, we will put it 0. If that's one text feature, we will put unknown. And mapping between all the data set, especially between the VCDB and AWIS. Then we will build then they build their model. The model they used is random forest classifier. Random forest classifier depends on many trees in many levels. So they use two level. First one is overall risk prediction. This is a binary. I think I explained in yeah. This is a binary classification to determine this our organization is a victim or not victim. It depends on 50 decision tree. The second level is conditional risk prediction. This depends on 20 decision tree, and each tree has about 25 sample because they avoid the overfitting. And this is conditional risk prediction because it depends on the conditional probability. So, for example, if we need to find the probability of physical drift, I draw this tree. If we need to know the probability of the physical drift, here we will find the probability of physical multiply the probability of drift given a physical incident. This is the second level of trees because, as I said, the first level is a binary trees to determine this is our organization or our destination device. Is it infected or not, or is it a victim or not, or non-victim? So, and the last step is evaluation. Like TPR, for example, if the true positive rate, this is correct. The result is correct, 90%. If it's false, and 10% is the result is not good or it is not accurate. The limitation here, we cannot predict all the incidents, such as social engineering and phishing. Like it will give low TPR, dependency on the data set. Already available on the internet. It's not some of data set are very old, sensitive to data quality. Sometimes once we did the pre-processing, we will manage the missing value in wrong way. That means we will get wrong result. And the data set doesn't contain information on the impact. This way it will predict this threat will attack or maybe it will affect our organization or not without any information about the impact or cost of the threat. And also here we don't have anything related to the evaluation or the validation validating and evaluating the result. There is no model, or they didn't mention anything how we can verify if the results are accurate or not. The last measure is integrated and hybrid approaches. This is depends on many techniques or many models from all the previous approaches. It's not there is no specific characters for this type of this approaches. So the method we can find the expert elicitation, fuzzy logic, attack tree, bias, statistical and probabilistic, everything. Here, Al-Hassan and other researchers suggest this model also has four main steps. At the beginning, there is expert inputs also. Fuzzy logic to convert the linguistic variable into numerical values. Attack tree to structure the attack process. And the bias network or also to calculate the probability estimations. Here, I think this is the main three I think like this it's clear. Here, this is the main three steps. The first one is analyzing artifact modeling. The second one, data generation. The third one, the security quantification. Each one of this calculated by a specific equation or specific concept, math concept. For that reason, I will not focus on the, I already mentioned all the equations, but it's not so important to focus on all of them. For you, or, by the way, not for us. This is, in the first step, security artifact modeling. It involves three main steps. First one is system description. Second one, attack tree modeling. At the end, translations of attack tree to Bayes network model. This is a transition between attack tree to Bayes network. Here, because as they mentioned, there is expert input, so we should to differentiate between the expert opinions. For that reason, they use the expert weighting, this formula, and also there is a table to score the expert opinion. Depends on the professional position and experience, qualification, and age. Here, to translate the linguistic variable into numerical values, to use a fuzzy scale, and then calculate the similarity between expert opinions, average agreement, and relative agreement. As I said, it's not so important to focus on all this math equation right now. Aggregation, then they calculate diffusification to calculate the area here. If we need to calculate the area between two opinions or between a group of opinions of experts. At the end, the probability of secure event we calculated using this formula. As I said before, the variable C represents the area or the distance between a group of opinions of experts. At the end, they calculated the probability of an attack by all the sub attacks or sub probability of basic attack. Using this top event probability based on AT model. For example, if we need to calculate the probability of MIM, we have to calculate the probability of BAS 1 and probability of BAS 2 using what we explained before. The limitation, high model complexity, depends on high quality expert judgment, because there is a scoring for all inputs. The result need also to be validated. A recap of key points. Multiple methodology exists to quantify cybersecurity risk. Each approach has unique strengths and limitation. In general, this literature doesn't suggest a best approach. Integrated models promise to address many challenges. So the research gap here, subjectivity, how we reduce reliance on expert scoring. If we can avoid the expert opinion at all, it's better. A static assumptions like alpha, beta, and weighting the opinions. Data quality and scale, especially for machine learning approaches. If we can increase the quality of inputs and increase the quality of data set. Real-time adaptability, because models always developing, so we need to learn to make it like self-adjusting models. Validation and verification, perhaps the biggest gap is testing. Most models are proposed without evaluation at all. The future direction, we will develop our own hybrid model with continuous learning and real-time data integration, automating expert input, reducing manual scoring. By technique, I suggested two techniques, like if we can use crawlers technique. This technique is used with the search engine, or NLP in security reports to feed models. At the end, we will build a model checker for testing, validating, and evaluating quantitative accuracy for our model. Here, because I'm studying now a course with Dr. Simon Tini, it's a part of my study plan here. Now we are studying the course which we are studying is computational models for complex system. So now we are studying how we can build a model checker, how we can check the model. This I will not talk details about this because still I'm studying and reading something related to. But to build a model checker, we should to understand. It requires to understand the model very well, and we have to understand which properties we need to validate, and depends on the model and properties we will build our algorithm to validate or to verify the properties, and we will depends on we will get a result. Is it okay or true, correct or not? If not, we will get counter example, and sometimes we will get a quantification result. This slide I didn't design it by myself. Actually, I could get it from this website. PCTL model. Yeah. Yeah, David here. I think this one. Yeah. For example, if we have a probabilistic model depends on Markov chain, and we have properties, temporal logic specification. Actually, the properties represent using PCTL, and then we will build our algorithm. Depends, for example, here Prism. So it depends on the model and the property. We will decide is it okay or not. If it's okay, done. If not okay, we will the algorithm will suggest a counter example, what we have to change or what we have to do to fix to make this property applicable with this model. Yeah, this is what I did, what I want to say.